All right, so this is the Edgenuity 6.3 section in the matrix unit called Scalar and Matrix Multiplication. It has two objectives: perform multiplication of a scalar and a matrix, and perform multiplication of two matrices. So let's talk about scalar multiplication first. Scalar multiplication is just a matrix times a number. And the typical notation is that we put the number first. Okay, we say the number times the matrix. And all this is just distribution. Okay, you just multiply it by every what we call element of the matrix. So like in number 1, we're doing 3 times the matrix 2, -1. This is a 2 by 1 matrix, just in case you didn't know that. We count the number of rows first, which are the horizontal part. So there's 1, 2 rows. And then we count the number of columns, which go up and down, and there's 1 column, so we have a 2. This is a 2 by 1 matrix because of that. 2 rows, 1 column. So we're going to make a new 2 by 1 matrix. When we do the scalar multiplication, your matrix size never changes. Okay? You just multiply the elements, and the answers go in the same corresponding spots. So this one is real easy. 3 times 2 is 6. 3 times -1 is -3. And there we have our new matrix after scalar multiplication. So same thing for number 3. By the way, this is number 1 and number 3 because these correspond to the problem numbers in a 4-problem set that you'll be doing in the videos. So same thing here, we just distribute the 3 to everything and make a new, this is a 2 by 2 matrix, 2 rows, 2 columns. So this 2 by 2 matrix, everything gets multiplied by that 3 right there. And we get 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, and we have a new matrix, 3, 6, 9, 12. So that's the real basics of scalar multiplication. It's just that easy. Now, matrices can be used to represent dimensions. One note, and I will box it in red here, one note that I want you to have because it's fairly important, is that note right there, which is that matrices can represent coordinates on the Cartesian plane, on the graphing plane, where every x and y, the x's are always the first row, the y's are always the second row, and the points are read by the columns. So in this one we have matrix A, which has a point x1, y1, and then a point x2, y2. Okay? But it can also be used to represent the dimensions of, say, a rectangle, like down here, where we have it representing the length and width of a rectangle. And so if I tell you that the length of this rectangle, hi Alicia, let me adjust your attendance. So we're representing the length of the rectangle in the first row and the width of the rectangle in the second row. Let me adjust this attendance. And so we've got this this rectangle represented by length and width, which we can represent those dimensions in this matrix. So matrix R, based on those things, would look like this. The length is 24 units, whatever those units happen to be, and the width is 18 units, whatever those units happen to be. Matrices are used in computer programming. You might notice this stuff looks a lot like spreadsheets, and that's no coincidence. Spreadsheets are versions of matrices, okay? So the question then is, what is 2 times R? So if we know R, then 2 times R is 2 times this 2 by 1 matrix, 24, 18. And then you just distribute the 2, so 2 times 24 is 48, and 2 times 18 is 36. And then the second question is, what does that look like? Okay, so what sort of a rectangle would you get when doing that? Well, you've got a new length here and a new width here. So it would be the same rectangle, except for the scale factor would be different. Now the length is going to be 48 and the width is going to be 36. So it's either you can think of it as a zoomed in version of the same rectangle, that is, you zoomed in by a factor of 2, making it twice as big on your screen. You can think of it as you made everything twice as big, that is, you stretched everything to scale to be twice as long and twice as wide. So if you stretch it by scale, that's where we get the term scale, because you're stretching it by a scalar. Okay? So that is the basics of scalar multiplication. The rest of what we're going to do is matrix multiplication, because it's quite a bit more in depth. Okay? So if you're watching, pay real close attention to these next boards, because they will, I hope, really help a lot. Okay? So matrix multiplication, it looks like A cross B, or just AB for 2 matrices, A and B. And if we have matrix A and B with their dimensions written out, and the dimensions are really important here, we have rows by columns for each one. So the multiplication A times B is only possible if the columns in the first row, or in the first matrix, equal the rows in the second matrix. In other words, I'm going to write this note and then I'll get rid of it, but I'm going to write this note. Order matters. So matrix multiplication is not commutative. That is, you can't do A times B and B times A and come out with the same thing, almost never. Okay? There are special cases where that happens, but usually if you do A times B, that doesn't even mean that you can do B times A. For example, if we have A as a 3 by 4 matrix and B as a 4 by 2 matrix, that means we're doing a 3 by 4 matrix if we're doing A times B times a 4 by 2 matrix. So we're going to do A times B like that. So what you do is you check the inner ones. Actually, let me do that in a different color. You check the inner dimensions, the ones right next to each other. If they're the same, then you are good to do the multiplication, and not only are you good to do the multiplication, but the resulting matrix, let's call it A times B, will have dimensions of the outer parts. Okay? So the inners have to match, and your resulting matrix will have the dimensions of the outer parts. Okay? So that's the basics of what the dimensions will be. Okay? So A might look like, if it's a 3 by 4, it might look like A, B, C, D, E, F, G, H, I, J, K, L. And B, if it's a 4 by 2, might look like M, N, O, P, Q, R, S, T. And then the resulting matrix would have answers in it, and those answers would look like, and I'm going to use a different notation here, would look like this: X1, X2, X3, X4, X5, X6. 3 rows, 2 columns. So that is, and remember, if there are questions, let me know, either unmute or put them in the chat. So that is how you know what the new dimensions are and what the matrix will look like. So then the question comes up, are these possible? So question A, let's write down what the dimensions are, and then we'll look at it. This first matrix, if you can see, is a 1 row, 2 rows, so a 2 by 1 column. Yes, I can go back to it. Give me one moment. So it is a 2 by 1, and of course the other one is also a 2 by 1. So let's review the rules. I'll go back to this so that you can look at it again. The rules are the inner numbers have to be the same, and the product, the resulting numbers, will give you the new dimensions for the new matrix. Okay, the outer parts will be the new dimensions for the matrix that you produce through the multiplication. Okay, so there's the rules. I hope I've given enough time to go back to the next one. Okay, I am going to go to the next slide again. Here we go. So then the thing I want to check is, are these two numbers, the inner numbers, are they the same? And clearly the answer is no. So this one is not possible. Let's look at B. Well, what are the dimensions of the first one? Well, we've got one row, so it's a 1 by something, and then we've got 1, 2, 3 columns, so it's a 1 by 3 matrix. Let me put that down a little bit lower, actually. So this is a 1 by 3 matrix. And then the other one has 1, 2, 3 rows. So it is a 3 by something. And then it's got 1, 2, 3 columns. So it is a 3 by 3 matrix. So look at the inner numbers. Are they the same? And the answer is yes this time. So is this one possible? And the answer this time is yes. That one is possible. And then I've got this other question down here. What size will the resulting matrix be? We'll talk about that in just a second. Let's do the last one. So what is the, excuse me, what is the size, what are the dimensions of the first matrix for choice C? There are 1, 2 rows, so it is a 2 by something matrix, and there is 1 column, so it is a 2 by 1 matrix. And then what are the dimensions of that second matrix? There is 1 row, so it is a 1 by something matrix, and there are 1, 2 columns, so it is a 1 by 2 matrix. Check the inner numbers. They are the same, and so C is also possible. Now, let's go back to B and answer the question, what would the dimensions of the resulting matrix be? What is the size of that resulting matrix? And for that, you just look at the outer ones. So I'm going to make a new matrix, and it's going to be the first outer number is 1 by the second outer number is 3. So it's going to be a 1 by 3 matrix. For C, same thing. Just use the outer numbers. It's going to be a 2, that 2 right there, by 2 matrix, that 2 over there. All right, so that is how you decide whether you can multiply matrices at all, and what the resulting dimensions will be. Now let's do an actual multiplication problem, and I'm going to show you how multiplication of matrices works. Now this is fairly complicated and fairly involved, so if you got questions, make sure that you let me know, okay? Here's how it works. You take, and I'm going to do this in a couple of different colors here. You take the first row of the first one and the first column of the second one. And first we should check, is this possible? So we've got a 1, 2, a 2 by something matrix, and it is by how many columns? 1, 2, 3. So we've got a 2 by 3 matrix being multiplied by a 1, 2, 3 by 1, 2 matrix. So our inner numbers are the same, so yes, we can do it. And now, give myself a little bit more room here. Now, how do we do it? So, you take, notice that we're gonna result in a 2 by 2 matrix. So, in order to create that 2 by 2 matrix, we're going to take the first row and the first column, okay? And what I'm going to do with those numbers is each one I'm going to do first number with first number, second number with second number, third number with third number, and I'm going to multiply each one, and then I'm going to add them all together. So it's going to look like this. Whoops. It's going to look like 1 times 1 plus 0 times -1 plus 1 times 3. And that is going to be the first element, first row, first column, for this new matrix. Okay? Let's look at a different color. And so then you're going to take, for the first row, second column, you're going to use the first row again. So I'm going to circle it in green this time, and the second column. And that's going to give you first row, second column. And you do the same thing. First number times first number, so 1 times -1, plus second number, so 0 times 2, plus third number, 1 times 4. Okay? And that actually completes my first row, because there's nothing left to do in the first row. So now let's look at the second row, and we're going to do the same thing. Second row, first column, is going to give us our second row, first column, and same thing, first number times first number, plus second number times second number, and so on. So that's going to be 2 times 1 plus -1 times -1 plus 3 times 3. And then I'll do the last one in purple. So we've got that same second row now times the second column to create second row, second column. So that's going to be first times first, so 2 times -1 plus second times second, -1 times 2 plus third times third, so 3 times 4. And then you do all that math and you get the answers. I'll do that real small, sort of small down here. 1 times 1 is 1. 0 times -1 is 0. So that's 1, 0, and 1 times 3 is 3. 1 plus 0 plus 3 is 4. 1 times -1 is -1. 0 times 2 is 0. 1 times 4 is 4. So -1 plus 4 is 3. 2 times 1 is 2. -1 times -1 is +1. 3 times 3 is 9. So that's 3 plus 9 is 12. And then 2 times -1 is -2. -1 times 2 is -2. And 3 times 4 is 12. So that's -4 plus 12 is +8. And there we have our answer. So I hope that gives you, we're going to do a couple more of these, but I hope that gives you an idea of how these work. Okay, that was a pretty straightforward example. Let's do something a little bit different here. What does matrix A look like? Okay, if I tell you that I took, okay, that A represents another matrix, and I took a matrix times that matrix A and I got this matrix here. Now, if you look carefully, the two matrices that are fully written out are the same, okay? Meaning, I multiplied two matrices together, got a new matrix, and the new matrix was the same as the first matrix. So let's look at a couple things. First of all, what are the dimensions of that first matrix? It's 4 rows, 4 columns, so it's a 4 by 4 matrix. I hope that you can see that. Let's look at the resulting matrix. It is also a 4 by 4 matrix. So what do the dimensions of matrix A have to be? Well, the inners have to match. The inners have to match, because if they don't, I can't do the multiplication at all. And the outer ones have to actually tell me the new dimensions, so it has to be 4 and 4. So matrix A is a 4 by 4 matrix. So that's the first thing I know. And then here's the way this works, and I'm going to sort of give it to you in the same way. We could go through all the math and everything, but the point is for you to see these types of matrices, okay? Here's the way this works. You would have a 1 in the first row, first column, element 1, 1, as they call it, and then all the rest would be zeros in the first row. In the second row, you would have a 0, and then a 1, and then a 0 and 0. The third row, you would have a 0, 0, and a 1, and a 0. And the fourth row, you'd have 0, 0, 0, 1. And if you look at this, you can see that the numbers run diagonally down the matrix. And so this is what we call a diagonal matrix, where all the numbers are in that diagonal running from left to right. And this type of matrix, this type, is called the identity matrix. And it's because when you take a square matrix, this only works with square matrices. When you take a square matrix and multiply it by the identity matrix of that same size, the resulting matrix, the product, is the same matrix as the one you started with. Now, this is a special thing where it actually is commutative. So if I did it in the other order, it would also work, okay? And if you want to explore more of that, you can explore it on your own, but those are the big facts that you need from that. So now we're going to talk about finding all the elements. And the elements is something that you will see in the first column, in the first section of this unit. You will talk about elements. And the idea is that these little sub numbers down here tell you what row and then what column each piece of the matrix, every piece of the matrix is what we call an element of the matrix. So what we want to do is we want to say, okay, if we have this matrix A here and this matrix B here, and we multiply them together in different orders, what do we get? And make sure we match things up, okay? So if I do A times B, first of all, that's a 2 by 2 times a 2 by 2. See, as you can see, our inner numbers are always going to be the same, and it will, of course, result in a 2 by 2 matrix. Those are the outer numbers. So if I do A times B, what will that be? Well, let's see. That's first row, first column, right? So it'll be 1 times 1, first row, first column elements, plus second number in the first row, -1, times second number in the column there, in the first column, 3. So that's going to be our first one. Second one is going to be like that. So 1 times 2 plus -1 times 4. So that takes care of our first row. Second row, we'll take second row, first column. So second row is 2 times 1, it's the first part of it, plus second row, second element, 1 times 3. And if you look at the way that I'm writing these, you'll sort of see patterns start to emerge on how you write them down and stuff like that. And you can use that or discard that as you are able to process it. Okay? And then we want to do second row, second column. That will give us our second row, second column element. So that'll be 2 times 2 plus 1 times 4. So if you put those together, that's 1 plus -3 is -2. That's 2 plus -4 is also -2. That's just a coincidence. 2 plus 3 is 5, and 4 plus 4 is 8. So we can write our matrix -2, -2, 5, and 8. And then what we want to do is we want to go up to what it told us about matrix AB and start corresponding things. So element C11 equals -2. Element C12 equals -2. C11 is that -2. C12 is that -2. Hope you can see that. C21 is 5, and C22 is 8. And I will leave the other direction for you guys to do in the, I can't remember whether this is an assignment problem or just one of the video practice problems, but I've done one direction for you. I'll let you guys do the other direction, unless somebody really desperately wants to see it. Let's do one more that we're going to involve both elements. We're going to do a scalar multiplication, and we're going to do a matrix multiplication. Now, the way this works is you have to do the scalar multiplication first. Okay? So I'm going to do the distribution first, and then I'm going to look at it again. So that'll be 9. 3 times 19 is 30, plus 27 is 57, and 3 times 12 is 36. So now I've got that new matrix times the matrix -1, -3, -5. Okay? So that's how we do that. And that's just we're doing it that way because that's the order in which it was written. Okay? Always work from left to right. So let's make sure that we can multiply these two matrices. This is a 3 rows by 1 column matrix. This is a 1 row by 3 columns matrix. Inners are the same, and we'll get out a 3 by 3 matrix. So it's not only is it possible, but it will result in a 3 by 3 matrix. So when we do this, we will do first row, first column. So our first element will be 9 times -1. Nothing to add it to because we don't have any more of those, right? Oops. Oh, I messed that up because I wanted to get rid of the circles. So 9 times -1. And that's the only one for row 1, column 1. That is element 1, 1. Then for element 1, 2, row 1, column 2, we'll do 9 times -3. Then for row 1, column 3, we'll do 9 times -5. And that's our first row. We've successfully done them all. For second row, first column, we'll do 57 times -1. That's a terrible 5. 57 times -1. For second row, second column, we'll do 57 times -3. And for second row, third column, we'll do 57 times -5. And finally, for third row, first column, we'll do 36 times -1. And third row, second column, we'll do 36 times -3. And for third row, third column, we'll do 36 times -5. And I'll leave it to you to do the math on those. The math isn't that hard on those. I will leave you with a little tidbit to think about. What if we had done the 3 times this one instead? Would it have turned out the same? So I invite you to just contemplate that. Just think about that. This is the final little note that I have for you. It gives you a matrix calculator in Edgenuity, but of course, for your future references, you won't have access to that matrix calculator. There is a matrix calculator on graphing calculators, and they're different to get to depending on what type of graphing calculator that you have. But for an online matrix calculator, if you go to meta-calculator.com, you will find different types of calculators, and one of them is a matrix calculator, and it works in much the same way that the Edgenuity matrix calculator works. It's got a few different little quirks in it, but I'm very confident that if you know how to use, if you figure out how to use the Edgenuity matrix calculator, you'll figure out how to use the meta calculator. That is all for this, so I am going to stop recording.